Hi everyone. Hello बच्चों. Sat Sri Akal and Namaste from my side. How are you all? So guys, this is Indrajit Singh welcoming you all into the most sensible platform and an excellence batch, right? Where awesome things appear. Okay, generally we used to start the physics like this way, right, into the very different manner, where live demonstrations are there, where solving examples are there, okay, where simulations are used to explain the concept, and things are gonna always quite easy. Right? So electrostatics got over, right? Electrostatics got over. Now this is a new thing that came up in front, that is electrostatic potential and electrostatic potential energy. This is a part of electrostatics, but generally it is taught with capacitors. Why? Because electrostatic potential energy, right, the capacitors is having the maximum use of electrostatic potential and electrostatic potential energy. Today's lecture is going to be quite small, don't get worried, okay, because only two things we are going to discuss: electrostatic potential, relation between the electric field. Okay, what will be the agendas of the today's lecture? Okay, we are going to see electrostatic potential energy, right? Second, we are going to see electrostatic potential. Okay, third, we are going to see electrostatic potential for dipole and for continuous bodies, right? And with relation between electric field and potential, V stands for potential. So this will be the agendas of today's lecture. Okay, it is not going to be right extend so much, else the students are going to get bored. Okay, it is not going to extend so much that right, the students are going to get bored. Immediately we'll slowly we'll cover up the all of those stuff, right? And guys, kindly stay till end. It is going to be the awesome thing. Okay, because if today's lectures you are right missing it out, then tomorrow, okay, you will feel what we can say the absence of it into the capacitors. When I'm going to teach the capacitors, you will feel the absence of this topic. If you're not aware of what electrostatic potential energy is, if you're not aware of what electrostatic potential is, right, then you will face a difficulty right into the capacitor. So today's lecture is important. It is a kind of a bridge between the electrostatics, right, the entire thing that we have seen into the previous lectures, and the capacitance, right? Okay, and the capacitance, right? Yes or no? Yes or no? Okay, so this will be the agendas of the today's lecture. Without wasting our time, we are going to start this stuff. Electrostatic potential and electrostatic potential energy. First, we are going to discuss the electrostatic potential energy and how we are going to define. See, let us take a very simple example to understand. This is the source charge and this is the infinity point where small test charge is kept. This is source charge. This is the point. Today it will be the freehand teaching. I have not brought any kind of the matter here. Okay, everything that will come up, it will come up naturally. The examples that are going to come up, it will come up naturally. Okay, it is generally called a freestyle teaching from our side, right? Totally free-handed teaching. If I'm getting this object in front, I can show up right you in front, okay, and it would be an example. Okay, suddenly an example, right, based on this, or any, what we can say, any situation from the day-to-day life based on this may arise, immediately I'm going to discuss, right? At any moment of time, freehand teaching means, right, we are going to give you all more than 100%, right, and you will enjoy it. Generally, students are in need of visualizations are not there. अच्छा लगता है, and it's not like that. Today we are moving forward to the freehand teaching style, right? Please have a note and pen with you all. Whatever the mandatory things are going to come, okay, just pause this video and note this down into a book. Okay, let's move. Electrostatic potential energy. This is a source charge. This is a charge at the infinity, right? Source charge, mother. Child, while playing a game, he is on an infinite position. Now, what happens here, right? What happens here? Mother told her child to bring up some stuff from a market, as of some, like, she got a news that some guests are going to arrive into the evening. So for that, she needs some food stuff. Okay. She requested once to her child. No. She requested second time to her child. Third time to her child. But all of those time, the child was busy into the, what we guess, in the call of a duty and all of kind of the games, or else he was, if he was not doing anything, then he was just scrolling out the Instagram pages. Okay. She got irritated. Immediately, she gave a task to external agent. Daddy. She gave a task to external agent that please bring up this child from infinite position to इंसानियत. उसको हैवानियत से इंसानियत में लेके आना मांगता. Right? Please bring that charge. He is into the infinite position. He never cares for anything. He's just revive kar, like that way. Okay. So she told to the external agent that please bring up the charge from the infinite position to somewhere into the point inside the electrostatic field of the mother. Let's say this is a boundary where the electrostatic force of this source charge X. Previously I told you this boundary is not fixed. This is just for the understanding purpose. Right? Boundary is not fixed. This is just for the understanding purpose. Child is out of his limits. Mother told external agent, dad, to bring up the child. Mother gave a task to a right husband, to the dad of a child, right? That bring up this child from the infinite position to the insaniyat. Let's say point P is an insaniyat. Right, where he is following right, what we can say, the rules of his mom and dad for his own good cause. Now, external agent did a smart work. Okay, let's write this down step to step. First, okay, source charge told external agent, external fallacy to do work. Right, external fallacy to do work. Now what external fallacy did a work in such a way, external agent did a work in such a way, it is important to tackle a child psychology, na? Right, it is important to tackle the child psychology. So he did very smart work. Slowly, he bring up the charge. He bring up the charge, right, to the point P in such a way that the velocity of the charge remains constant. Slowly, bring up the charge from the infinite position to the insaniyat. Right. Now, external agent did a work in such a way that velocity of the particle remains constant and change in kinetic energy remains zero. This field is conservative field. So whatever the work is done, okay, whatever the work is done, right, for a conservative field, right, it is always stored into the form of the potential energy. According to the work energy theorem, W is equal to delta K plus delta U. If external agent is doing the work, it means that kinetic energy is zero, then only we are having the potential energy. Here, this potential energy is defined as electrostatic potential energy. The actual definition lies behind. The actual definition lies behind the work done by external agent to bring up the charge from infinite position to the point under the electrostatic field. Work done by, see, W is equal to delta K plus delta U according to the work energy theorem. I told you all. So here, whatever the external agent is doing the work done by external agent in bringing up the charge from infinite position to point P. This is defined as the energy needed for that. Electrostatic potential energy. A unit is joule, right? Unit is a joule, and electrostatic potential energy is nothing else but a scalar quantity. There is a very small difference between the electrostatic potential and the electrostatic potential energy. Very small difference, right? So the definition of this is a mandatory part. Please guys, mark my words. If you want to note this down into the book, immediately do that, right? Work done in bringing up the charge. This is a smartness of the external agent. Smartness of the external agent states that work done in bringing up the charge slowly, smartly, psychologically from the infinite position to the point under P. Then this kind of the thing it is, right? Electrostatic. The energy in it, required in it, then this entire phenomena, right? Work is done, it is stored into the form of the potential energy. Why it is stored into the form of potential energy? Because the field is conservative. And this thing we have discussed into the work energy and power 11 standard 6 chapter, that whenever the work is done into the field, the conservative field, right, or conservative forces are involved into it, like mg, weight, right, the gravitational forces, okay, the spring force. At that time also I told you all, it was the electrostatic force. So whenever this kind of the forces does the work, it is always stored into the form of the potential energy. Against mg we are having gravitational potential energy. Against restoring force kx we are having elastic potential energy. Again, this for this in electrostatics, against the electrostatics force we are having the electrostatic potential energy. So whenever this work is done, it is stored into the form of the potential energy, right? Okay, so this was the electrostatic potential energy. Now how the electrostatic potential energy for the single charge and for the n charges it is defined, right? Generally electrostatic potential energy only for the n charges are defined, okay? And how I told you all, work done is associated with, right, the change in potential energy of the system, right? Work done is associated with the change in potential energy of the system. Yes or no? Right. Then we are going to see how it is defined for the n charges, right? And how it is defined for the, okay, please allow me. Okay, please. Paste. Paste. We are going to see some example based on this formula. Okay, I heartily apologize for this. Right, went on. Okay. Work is done. Now, electrostatic potential energy for the n charges and how work done are involved into it. First of all, let's say one system of the configuration it is given. Okay, 4 charges are kept on the vertices of the equilateral triangle. This square. Sir, this does not seems to be square. It seems to be rectangle. Thoda adjust kar lo yaar. Okay, length is L. Okay, now what will be the resultant potential energy of the system? What will be the resultant, right, a potential energy of this system? See now, this thing we have seen into in gravitation. Generally what we used to do in gravitation, okay, we used to calculate the number of the pairs, and on basis of that, right, we used to apply into n into n minus 1 formula to know how much number of the pairs into the expression of the electrostatic potential energies are there. This thing we use into the gravitation. We did into the gravitation. Okay. So here, the resultant potential energy on this system, it is nothing else but, let's name all of those charges. This is charge 1, this is charge 2, this is charge 3, and this is charge 4. Okay, 4 charges are there. U 1 of 2, 1 of 3, 1 of 4, 2 of 3, 2 of 4, 3 of 4. Right? 1 of 2, 1 of 3, 1 of 4, 2 of 3, 2 of 4, 3 of 4. Right? Everyone? Okay. This is how the pairs are defined. The same thing we have did into the, right, same thing we did into the gravitation, and right, the same approach we are following here. But in gravitation, the potential energy is always negative. Here, the positivity or sorry, the convention of the potential energy completely depends on the charge configuration. Right? Configuration. At that point in the gravitation, potential, all of those equations of the potential energies are negative, right? The maximum value of the gravitational potential energy was 0, right? And rest of all of those values were negative. But here, right, at that point of time, we were having only the attractive force into the nature, that was gravitational force. Here we are having attractive and repulsive forces. So depending on that, right, the value of the potential energy differs, right? Value of the potential energy differs. So here, U12, U13, U14, U23, U24, U34. Okay. So the resultant potential energy system that can be given as K Q1 Q2 whole divided by L, K Q1 Q3 whole divided by L root 2 plus K Q1 Q4 whole divided by L, right, plus K, right, Q2 Q3 whole divided by L plus K Q2 Q4 whole divided by L root 2, right, plus K Q3 Q4 whole divided by L. All of those identical charges are there, so it's K Q square L is common, right? Then that is 1 plus 1 by root 2, right, plus 1 plus 1 plus 1 by root 2 plus 1, right? So U R, that is equal to K U square by L 4 plus 2 by root of 2, right? Okay. So if we are making up this 2 as common, then it is 2kq square by L 2 plus 1 by root of 2. This is the resultant potential energy of the system, right? The resultant potential energy of the system, right? Even here you can replace the value of the K and do that stuff, right? Yes or no, guys? Okay, so this is the result, and this is now this was the procedure I told you all for the calculation of the electrostatic potential energy, but how we can correlate it to the work done? How we can correlate it to the work done? Now let's see. Okay, let's see some examples. Okay, three of the charges are placed on the vertices of the equilateral triangle. Three of the identical charges are placed on the vertices of the equilateral triangle having side length L. What will be the work done by external agent? What will be the work done by external agent, right, to reduce the size of triangle by L by 2? We want to reduce the size of this triangle. Initially the size is this, right? We have to reduce the size to L by 2. Positive charge, right? Then how much external agent has to do a work so that the system can transform from the side of the length L to L by 2. Okay, system can transform its side from L to L by 2. Again, we are going to come back to the theory. Okay, again we are going to come back to the theory. What kind of the theory? If external agents does the work, right? Mark my solution for it, right? If external agent does the work, if external agent does the work, it does in such a way, right, that change in kinetic energy is 0. Work done by external agent, that is delta K plus delta U, right? Okay, slowly it reduces the length of the triangle. Okay, so here work done by external, that is U final minus U of initial. Through this formula we are going to evaluate this stuff, right? So work done by external agent, first of all we are going to write down the final. 3 pairs are there, 1 of 2, 1 of 3, 2 of 3. Okay, this is a final minus initial, right? 1 of 2, 1 of 3, 2 of 3. Resultant potential energy final minus resultant potential energy initial. Okay, so this is going to be kq square by L square. This is 3 kq square by L by 2, right? Okay, 3 kq square by L, right? Okay, so this is going to be 3 kq square by L. This much amount of the external agent, right, has to do a work. Sorry, 6 minus 3 is 3. Okay, right? Yes or no? Okay, so this much amount of the external agent has to do a work. Now students might be thinking, sir, this is only the same sort of example and it appears quite easy. Okay, it appears quite easy in front of us. Okay, now let's have another example of an external agent to do so. Okay, suppose okay, let's change the configuration of the system, right? Let's change the configuration of the system. 4 charges are present, right, and the vertices of the square. 4 charges are present at the vertices of the square, right? Plus q, plus q, plus q, plus q. This we saw. How much amount of the external agent, right, work external agent has to do to transform its into like this way. This is 2L and this is L, plus q, plus q, plus q and plus q. right? How much amount of the work external agent has to do? How much amount of the work, right, an external agent has to do, right, to transform the system from this to this, to transform the system from this to this. Okay, so now what we are going to do here, it is very simple. Work done by the external agent, that is equal to change in kinetic plus potential. External agent does the work when the change in kinetic energy is 0. So here the external agent, that is equal to delta of U, right? Okay, so here okay, what is the U final? See, 4 pairs are there. Okay, so it would be k q square, or you can directly write it down as, if it would be quite confusing, right, then it is U 1 of 2, U 1 of 3, 1 of 4, 2 of 3, 2 of 4, 3 of 4 final, minus same for initial, right? So work done by external agent, it is going to be what, right? Work done by the external agent, it's final is, okay, let's name it 1, 2, 3, 4. Okay, in between 1 and 2 it is kq square by 2l. Okay, in between 1 and 3 it is kq square whole divided by, now this is gonna be weird, and this is under root of 5l. 1 of 4 kq square by l, right, and 2 of 3 kq square by l, 2 of 4 kq square by under root of 5l, right, plus 3 of kq square by 2l, right, minus, right, kq square by l, right, this thing we have already calculated. For a square we have already calculated, it is 2 kq square by l, right? For a square we have already calculated, let's write it down into the previous slide only. For a square we have already calculated, right, minus 2 kq square whole divided by l, right, 1 or 2 plus 1 by root 2, right? So 2 are we having 2l, 2 of l and 2 of under root of 5l. So the work done by the external agent, it will be 2 kq square by l, 2 kq square by 2l, 2 kq square by under root of 5l, minus, right, 2 kq square by l, 2 plus 1 by root 2. Okay, so what will be the work done by the external agent, right? 3 kq square by l plus 2 kq square by under root of 5 of l, right, minus 2 kq square by l, 2 plus 1 by root of 2, right? And if you want to make these things as a constant, then it is kq square by l, 3 plus 2 by under root of 5, right? Okay, and minus 4 plus, sorry, not plus, minus 4 minus 2 by root of 2. So this is gonna be kq square by l, 2 by under root of 5, okay, minus root 2 minus 1. This will be the work done by the external agent, right? Okay, this is how things are gonna get calculated into the electrostatic potential energy. Okay, this is how things are calculated into the electrostatic potential energy. Sir, you haven't taught the actual definition of, see now here we can do this. If external agent is not doing a work, right, then there is a possibility as because of the mutual force of attraction they are coming near to each other. So there are some applications in which the kinetic energies are also involved, right? But being right at the beginners level, slowly we are trying to grab up the concept. So for at this moment, this much is enough. Slowly when the practice questions and the PYQs will come up now, in that we will see the questions in which the kinetic energies are also involved. Okay. Now some students might be into the thought, sir, you haven't taught us generally the electrostatic potential energy and the electrostatic potential, right, are taught with respect to each other only, right? Then how you forget this part, right? Okay. Electrostatic, see now in the today's lecture, the remaining part is electrostatic potential for the n charges, for the dipole and for the continuous bodies, and the relation between electric field and potential. It seems to be, yes, it seems to be as much easy as you all are thinking. Generally students are having a myth, right? They are having a myth that electrostatic potential energy higher potential, oh like that. No. Right. So what happens here? Electrostatic potential, same procedure is there. Okay, there is a very small difference. Again, I am taking one source charge mom at infinite small charge is kept. Electrostatic potential, it means that electrostatic potential, it means that work is done bringing up the work done by external agent in bringing up the charge. I'm sorry. Bringing up work done by external agent per unit charge. Work done by the external agent per unit charge. Is it possible that at the infinite position only single charge is present? No. N number of the charges are present. Into the previous example you told, right? I told you all. See, my question is how this configuration is formed. External agent might have done the work, na? Let us take an example. All of those 4 charges are present into the infinity. All of those 4 charges are present at the infinity point. What does the external phalancy or external agent does? Slowly they are bringing up one charge from the infinite position to the point. Slowly they are bringing up the charge from the infinite position to a point. Slowly they are bringing up the charge from the infinite position to a point. Right? So how this system is formed? Previously they were having n number of the charges at the infinite position. Among all of those n charges, external agent bring up the 4 and form this kind of the configuration. So the potential energy is associated with the entire system, but the potential energy or the work done is associated with the entire system. Yes, we brought up the 4 charges, this much amount of the work done, and this was stored into the resultant potential energy of the system. But what about the work done in bringing up only single charge from 4? Work done in bringing up only a single charge from the 4 or from the n number of the charges. So that is nothing else but an electrostatic potential. Okay, this is right a point. Suppose this is a boundary of an electrostatic field, right? External agent does the work in such a way, right, that change in kinetic energy remains 0. Change in kinetic energy remains 0. Okay, change in kinetic energy remains 0. Okay, so work done by the external agent per unit charge. Now this work done per unit charge is defined as electrostatic potential. This whatever amount of the work is done, it is stored into the form of the electrostatic potential energy, EPE, It stands for electrostatic potential energy. So can we define it as a delta U by Q? This is nothing else but the electrostatic potential. You can understand the difference. Generally, student fails to understand. Why? Because whenever they are dealing with this kind of this stuff, the definition seems to be quite similar, right? Definition seems to be quite similar. So this is how the potential is associated. Work done in bringing a single charge from the infinite position. Likewise, we calculated the potential for the single charge for the, we calculated the potential energy for the system of the configuration, right? And we calculated for the n charges. Similarly, we can do it for the electrostatic potential, right? We can calculate the resultant potential energy of the system. Okay, the same we can do for the. Now, here comes the new concept, but this we are going to see afterwards. Okay, first of all, it is important to understand what actual the this electrostatic potential is all about. Okay, electrostatic potential due to the n charges. First, suppose the configuration has, right, plus Q, negative Q, plus Q, plus Q. We need to calculate the potential at the point P. Okay, there exists a strong relation between the electrostatic potential and electric field, mark my words, right? There exists a strong potential, right? There exists a strong relation between the electrostatic potential and the point charges. There exist. Okay, so here what happens? If you want to calculate the resultant potential, then it is potential is because of the first, second, third, right, and fourth. For positive, it is the potential is also the scalar quantity, right? So the resultant potential, I can write it as kq by, let's say this distance as a, right, plus kq by a minus kq by a plus kq by a. This thing is going to get cancelled. The resultant potential of this system is 2 kq by a. Okay, this is how, right, analogy to the electrostatic potential energies, right, analogy to that the electrostatic potentials are calculated. For the single charge, it is kq by, right, distance a. For the point charge, another definition of the point charge, it is v is equal to delta u by q, right? For n charges, kq1 by a1 plus kq2 by a2 plus dot dot dot, it extends up to n values, right, depending on what kind of the configuration it is there. Okay, now electrostatic potential due to the conducting sphere, right? Before moving on to the conducting sphere, let's move on to the dipole, electric field due to dipole. Okay, one thing is missing here. Okay, let's add this up, right? Oh, electrostatic potential is because of the dipole, right? Suppose if I'm talking about the two positive, one positive and a negative charge, they are separated by the distance L. At any general point P, as because of this dipole, I need to calculate, right, the electrostatic potential. At any general point P, what is our agenda? At any general point P, we need to calculate, right? At any general point P, let's say this midpoint is, right? Can we name it as R1? Can we name this as R2? Can we name this as R? We are having a very simple concept. It is K Q1 by R1 minus K Q2 by R2. The resultant potential energy is KQ1 by R1 minus 1 by R2. This is as much simple as what we are thinking, but it is important to understand, right? It is important to understand, okay, how to calculate R1 and R2. To calculate R1 and R2, let's say this is theta, we need to drop a normal. One normal, I am dropping like this way, right? This distance is 2L, I must say this is L and this is L. The second normal I am dropping like this way, 90 degree, right? I have drawn two normals, right? R2, right, will be calculated using this normal values or this dropped normals. Okay, suppose this is L, right? Suppose here this is L, this is theta, then this thing is gonna be L cos of theta. Similarly, this thing is also gonna be L cos of theta. If I want to calculate R1, I can say R plus L cos of theta. R2 I can say R minus L cos of theta. Using simple geometry by dropping up the normals, right? Okay, now some students might be in a thought, sir, how we got this, right? See, this is L, this is theta, this is 90 degree. So as of that reason, this is gonna be L cos of theta. Okay, this is a small triangle. Okay, the magnified view is here. Magnified view is here. Yes or no? Can we replace all of those equations here? So to reach up to these results, okay. So finally it states that V is equal to K of Q1 minus, right, what is the value of R plus L cos of theta minus 1 by R minus L cos of theta, right? So it is V is equal to K of Q. If we are evaluating this, then minus 2L cos of theta, right? I heartily apologize for that. Okay. Okay. So this is gonna be R square minus L square cos square theta, right? Resolving this A square, A plus B and A minus B. So it's A square minus B square like that. Right, so it is V is equal to 2KQL cos of theta whole divided by R square minus L square, right, cos square theta. So this is gonna be the net potential, right, for S because of the dipole. Okay, net potential S because of this dipole, right? Okay, so here okay, electrostatic potential. So this was as we first of all we saw for the single charge, then we for the n number of the charges, and then we saw for the dipole. Now it's time to move on for the electrostatic potential for the continuous bodies like conducting sphere. See, electric field we calculated for the long charge, right? For all of those cases, right, we can calculate, right, the electrostatic potential. But here it is important to understand the relation between the electrostatic potential and electric field. So for that, first of all, we are directly moving on to that relation, and at the end we are going to discuss this. Equipotential surface. Surface at all points with the constant value of potential. It is equipotential surface. Suppose this is the equipotential surface. How I can declare this? Okay, so it's a very simple stuff. Potential at each point on the surface remains constant. Potential at each point on the surface remains constant, right? This is nothing else but n, the equipotential surface. Potential at each point remains constant. Okay. Lots of equipotential surfaces are there. If I want to compare, if you want to understand this right concept to the day-to-day life example, you have thrown the this into the water. Okay, the stone into the water. We have already thrown. So whatever the ripples, right, they are generated. Okay, and you can understand there are lots of spherical shapes. Smaller one with the larger radius, again with the larger radius, again with the more large, right, more radius. Okay, so each of this small individual part, we can say it is an equipotential surface, and this thing we have discussed even into the fluids 11 standard chapter number 10 or 11, right? The lots of equipotential surfaces are there, and equipotential surfaces always see there exists a relation between the electric field and the potential. There exists the electric relation between electric field and the potential. How? First of all, let's understand the example of the equipotential surfaces. See, this is the best example. There is a possibility if we are having the 4 equipotential surfaces, then 4 of them might be having the different value of the potential. There is a possibility that if we are having the 4 equipotential surfaces, right, then there is a possibility that each individual equipotential surface might have the different value of the potential. But it is not possible that at each point of that equipotential surface the value is gonna get changed. At each point of that equipotential surfaces, the value is not going to change. If I'm talking about the first equipotential surface, then value is going to be V1 only, V2 only, V3 only, and V4 only. Okay, V1 only, V2 only, V3 only, and V4 only. Okay. Second type of equipotential surface appears like this way. This all are equipotential surfaces with the value V1, V2, V3 and V4. This all are also equipotential surfaces. This kind of the ripple effect is generated all the time, V4, V. This all are also the equipotential surfaces. So this is a definition of the equipotential surfaces, and these are some sort of examples for it. Okay, some sort of examples for it. Okay, the definition of the equipotential surfaces and some sort of examples for it, right? Some sort of examples, right, for it. Now, how these equipotential surfaces are obtained and how to identify the relation between electric field and potential. Suppose if I'm talking about the equipotential surfaces, right, like this way. Okay, I'm just taking this. The distance between the equipotential surfaces, it is delta R. Distances between the two equipotential surfaces is delta R. Can I say this is V1, right? This is V1 plus delta V. Okay. So the relation between the electric field and the potential is E is equal to negative of del V by del R. For a very small change, E is equal to negative of del V by del R. For a very small change, E is going to be negative of del V by del R. Yes or no, guys? Okay, negative of del V by del of R. This is generalized form. You can even evaluate into the vector form also, but slowly we are going to see that into the examples. Difference between the two equipotential surfaces is negative of V plus delta V minus V whole divided by delta R. So this is E is equal to, you can say it as, sorry, du and dr. Let's name it as dr. Okay, so it is E is equal to negative of d of V by d of R. This is for the very small change, and obviously the equipotential surface, right, the distance between two is quite small. For the numerical explanations we are having in centimeters, but generally distance between the two equipotential surfaces is quite less. Most like noteworthy points regarding the relation between, we got this relation. If you want to write down into the vector form, then it is Ex of I, Ey of j plus Ez of k. Similarly, you can write it down as a negative of del V by del X of I, right? Negative of, I'm sorry, negative of del V by del X of j, negative of del V by del, sorry, this is y, z of k. Okay, this is defined into the vector form. Okay, this is the thing that is defined, right, into the vector form. Noteworthy points regarding the equipotential surfaces, right? Noteworthy points regarding the equipotential surfaces. First, electric field is always perpendicular to equipotential surfaces. Direction of the electric field is always from higher to lower potential. Direction of electric field is always from higher potential surface to lower. Right, higher potential surface to the lower. Okay, so these are the two most worthy points related to the relation between the electric field and the potential. Now let's see some of the sums based on it, right? And finally after that we are going to see, right, now see, suppose if the potential value is given as phi x square minus 2, right, calculate the value of the electric field, right, at 0, 1, 1. Potential depends on the distance as like this way. Calculate the value of the electric field at 0, 1, 1. Into the vector form, electric field is defined as Ex of I, Ey of j, Ez of k. Right. Now what happens here? Here we are having only the value of the V that depends on X. So Y and Z doesn't matter. So this is going to be del V by del X of I. Can we say it is partial differentiation del V by del X phi x square minus 2 of I, right? So that is equivalent to electric field is a negative of 10x of I, right? So this electric field, it is given as negative of 10x. It means we want to calculate the value of 0 Newton per coulomb. We need vector I. Why? Because its x coordinate is going to be 0. This is V depends on X. Suppose if the potential is given as (3x square minus 2y plus 4z), potential depends on X also, Y also and Z also. Then how we are going to calculate the value of the electric field? Ex of I, Ey of j, Ez of k. Ex of I, Ey of j, Ez of k. Right? First point. Del V by del of x, right? 3x square minus 2y plus 4z. There is a slight difference between the partial differentiation and the differentiation. If we are differentiating this now, then chain rule is applied. We can differentiate y with respect to x, we can differentiate z with respect to x using chain rule. It is possible. But whenever this del symbol is there, na, it means we have to do partial differentiation. Generally for the conservative fields, right, partial differentiation needs to be done. In partial differentiation, no chain rule is there. Okay, in partial differentiation, no chain rule is there. It means if you are differentiating with respect to x, rest of them are constant, so it is 0. So if we are differentiating this with respect to x, is 6x minus 0 plus 0 is equal to 6x. Suppose if you are differentiating with respect to y, okay, then it is equal to negative of 2 plus 0 plus 0. So it is negative of 2. If we are differentiating with respect to z, then rest of the things are constant, right? So it is plus of 4. Now what is an actual equation of the electric field? That is Ex of I plus Ey of j plus Ez of k. It's negative of del V by del x of I, negative of del V by del y of j, negative of del V by del z of k. Okay, so this is gonna be negative of 6x of I plus 2, right, of j minus 4 of k. Mark my words, you will always get confused into the plus and negative signs, right? So please take care for this. Now suppose if we want to calculate the electric field at 1, 1, 1, right, replacing this electric field at 1, 1, 1 is negative 6 plus 2 minus 4 j k. Okay, you can find this magnitude. What happens when graph is given? Electric field versus x graph, right? And second, potential versus x graph. Right, a plus 10 Newton per Coulomb at the distance of 5 centimeter. If it is E versus X graph, area gives E delta X, that it gives potential difference, right? Area gives potential difference. So that is gonna be E is 10 Newton per Coulomb into 5 centimeter, right? Okay, so this is going to be potential difference. This is going to be 50 into 10 to the power minus 2 volt. If it is V versus X graph, then slope gives electric field. Del V by del X is a slope that is equal to 10 of theta, and that is equal to 10 of 30 degree. But electric field is negative of slope of del V by del X. Mark my words. Electric field is negative of the slope. Negative of the slope. So here, right, the electric field is going to be negative of 10 of 30 degree. Is negative of, right, 1 by root 3 Newton per Coulomb. This is how the relation between the potential and electric field is calculated using graph. Now another thing that comes upon the variety of the question. This distance is 10 centimeter, this is 10 volt, this is 20 volt, 30 volt, right, 40 volt. What will be the direction of electric field and its magnitude? The question is having this kind of the configuration. We need to calculate the electric field direction and magnitude. Electric field direction and its respective magnitude. Sorry for this. Right? Electric field direction and its magnitude. Just hold on, guys. Sorry for this. I'm having an itch. Right? Just hold on, please. Right? So, I told you all electric field is always perpendicular to the equipotential surface. Right? Suppose this theta is given as 30 degree. Right? Okay, this is 10. Can I say this is 10 sine of 30 degree? Okay, this is 10 sine of 30 degree, this is 90, and this is 10 cos of 30 degree. The distance that is exactly perpendicular between the two surfaces, it is calculated. Suppose if I want to calculate the electric field, that is delta V by del of R. Right now I'm taking it as a magnitude. What is the potential difference between the two equipotential surfaces? That is 20 minus 10 whole divided by what is in a perpendicular distance. Right, this delta R is a perpendicular distance between the two equipotential surfaces. So this is going to be 10 sine of 30. So this is going to be 10 by 5, 2 Newton per Coulomb. But I think this is into the centimeter, so it is 10 to the power 2. So it is going to be 200 Newton per Coulomb. This is the right magnitude of electric field. What will be the direction of this electric field? It is always from the higher to lower potential. Right, direction of the electric field is always from the higher to lower potential, or in another sense we can say in the direction of the electric field for potential decreases. So direction of the electrical field is from A to B or B to A? Yes, obviously it is from the B to A. In direction of the electric field is of the magnitude 200 Newton per Coulomb. Right, okay, so this kind of things are always that. Okay. Electric field for the conducting and the non-conducting sphere. In conducting sphere, if I'm talking about the conducting sphere, then charge only resides on the surface. Right? Using Gauss law, we are taking one Gaussian surface of the radius r. Right? And we are going to plot the graph V versus R. First point, V inside, electric field inside the conducting surface is 0. It means that negative of del V by del R is 0. Differentiation of any physical quantity is 0. It states that potential is constant inside the sphere. Throughout the sphere, right, from the inside area, the potential is constant. Why? Its differentiation is getting 0, that is equivalent to the electric field. At the surface, we are having no choice, that is equal to kq by r. Right, and suppose if you are taking the Gaussian surface with the larger surface area, right, smaller. Then at the outside, this is value at inside, this is value at the outside. It is kq by smaller. So when r is less than r, when r is equivalent to r, when r is greater than r. When r is less than r, potential is constant. At surface, it is kq by r, and after that it decreases with respect to, it follows the inverse relation. Graph is like this way. Right? Graph is like this way. Yes or no, guys? Okay, the same thing we did into the electric field using the Gauss law. Okay, the same thing we did into the electric field using the Gauss law. Okay, now things get deferred, right? Things get deferred, right? If we are directly moving forward, right? If we are directly moving forward to the non-conducting surfaces. For a non-conducting surface, the sphere, okay, for a non-conducting sphere, what happens here? Again, we have to take one Gaussian surface. Inside the radius is r. Non-conducting sphere is having the inside, right, and outside on the surface. It is having the charge distribution inside and even on the surface. So first, this is a graph, right? Inside, electric field varies as kq whole divided by r cube into small r. This electric field equation we have calculated using the Gauss law. How we are going to calculate the, right? How we are going to calculate the potential using the relation between the electric field and electrostatic potential. Okay, E is equal to negative of del V by del R, right? V is equal to negative of E dot del R, right? So can we say that V is equal to negative of integrating from, okay, small r to capital R, electric field is kq by capital R cube into R of d of R. Okay, R of d of R. So now resolving this, we get, before resolving this, here we are having right, the potential difference, right, in between V minus Vs. This is a point minus surface. So this is going to be V is equal to Vs plus, right, kq by R cube is going to constant R of dr moving on from small r to capital R. Right, it is V of S plus kq by R of cube limiting from R square by 2 small r to capital R. If I am replacing this as kq by capital R, kq by R of cube, right, R square by 2 small r to capital R, then inside, right, into the conducting sphere, the equation comes out to be kq by 2r 3 minus small r square by capital R square. This is the value of the potential inside, right? At the surface, it remains same. V is equal to kq by r. Outside at any point, right, that is at the distance r, it is kq by small r. It doesn't matter, right? It doesn't matter. Okay. Now here, how the graph is changing. Inside we are having the variations, right, like this way. Suppose if you want to calculate at the center, keep the value of the R at 0, then you will get the electric field, value of the potential at the center. If we are making value of R as 0, then we are going to get 3kq by 2R. Right? Surface, we are having the value of kq by R. It means till surface, right, the value decreases like this way. From at center 3kq by 2R, at the surface kq by R, right? So the value decreases, right, from the center to the surface. And slowly here at the surface it is kq by R, outside V is inversely proportional to R. So it follows like this way. This is a graph for the non-conducting surface, potential for the non-conducting surface, right? Potential for the non-conducting surface. Similarly, we have to follow for ring, right? Similarly, we have to follow this thing for ring, right? The same thing you can do, the ring having the uniform surface charge density as lambda, right? At the point P at the distance x, you need to calculate the potential. For this, we are having the equation of the electric field. Equation of the electric field at the point P, that is kqx, right, whole divided by r square plus x square whole to the power 3 by 2, right, into unit vector n. Suppose you want to calculate the potential, then it is E dot del of r. This integration is going to be quite difficult, right? Moving on from 0 to r, this integration is going to be quite difficult, right? So rather than to move on to that directly, we are accepting this equation, right? It is 2 pi k lambda, right? Okay, under root of r square plus z square whole to the power r, right? 2 pi k lambda r, okay, 2 pi k lambda r whole divided by under root of r square plus x square, right? This is the equation of the potential at the point P as because of the ring. Okay, I'd be that much is enough for this today's lecture. Okay, again we are going to do some sums into the practice, but tomorrow, guys, please mark my word, tomorrow, right, a new thing we are going to start, that is a capacitor. It is quite different types of capacitor we are going to see. We are going to see the capacitor device. Okay, so please be attentive and mark up to that. Okay, so I'll be waiting for all of your comments beneath the video regarding the electrostatic potential and potential energies. Tomorrow we are moving forward to the capacitor. So guys, it's time to go. Again, we'll come back tomorrow. This is Indrajit Singh signing off from the desk. Bye bye. Sat Sri Akal and Namaste from my side. Bye everyone. Stay at home, stay safe, stay healthy, Mrs. Bye bacha ji.